Okay, yeah, please watch the lecture video I post on the discussion board for the day. And I don't think I can finish all these topics in one day though, especially in 80 something minutes. I don't think it's doable. But at the same time, if I really need to do everything in class, then will be too far behind. Okay, so please help yourself to watch those lecture videos such that then we can have more time to do problems. Okay, now we will start with polynomial. What is a polynomial? Definition. Polynomial is a function. Well, I think I should say polynomial function instead of just polynomial. Polynomial function I denote it by px. You can use fx, of course. Okay, but I purposely use capital P for polynomial in my class to emphasize that's a polynomial. Okay, polynomial px is a function with form, with the following form. Px is equal to a subscript m of x to the n plus a subscript n minus 1 of x to the n minus 1 all the way to a subscript 2 of x squared plus a subscript 1 of x to the 1 invisible 1 plus a subscript 0. Yeah, for example, if we have px equals to 3x to the 5th minus 7x to the 4th plus 2x cubed minus 8x plus 4. Let's say we have something like that. Now then, from here, can you tell what is the n? The n is the exponent, the highest exponent. Okay, n is the highest exponent, that's 5. We also call this the degree of the polynomial. N equals to degree of px. Okay, the highest exponent in that polynomial is called the degree of px. Now then, how about a sub 5? Now, a sub 5 is the coefficient of the term with degree 5. So if this is 5, then this is a sub 5. Okay. A sub 4 is the coefficient of the terms with degree 4. So a sub 4 will be -7. Are you with me? How about a sub 3?
2.
That's 2. Okay, how about a sub 2? Nothing, right? So it's 0. A sub 1 is -8. A sub 0 is 4. Okay. Now, if n is the degree of px, then a sub n is the leading coefficient. We call that the leading coefficient. Coefficient for the term with the highest degree is called leading coefficient. Now, leading term, a sub n x to the n, is the leading term. Okay, so in this case, the leading term is 3x to the fifth. Okay, now a sub 0 is also called the constant term, or simply just the constant. Now, the domain of a polynomial, as we have known, the domain of any, not only a polynomial, of any polynomial is all real numbers, because we can plug in any numbers to the polynomial and the output still a real number. Okay? In fact, we can say more that the y-intercept of a polynomial is 0, a sub 0. Right? So for this polynomial here, the one we have up here, if we try to graph that later on, which is the main purpose of this chapter, to graph the polynomial. Now, so this polynomial here in the example, the y-intercept will be 0, 4. Okay, now next. Px with degree n has n zeros. Now, what is zeros? For now, you can say zeros similar to x-intercepts. Maybe I just tell you right away what is a zero. Definition: the zero of a function, maybe I should say c is a zero of a function fx if fc equals to 0. So just to explain that terminology, suppose I have fx equals to x squared plus, minus 4. Then we say the zeros are x equals to 2, x equals to -2. Now, why? Because f2 equals to 0 and f -2 also equals to 0. Okay, now you will see later on that x zeros is related, very heavily related, very closely related to x-intercepts, because if the 0 is a real number, like in this case, then the x-intercepts are 2, 0, -2, 0. If the 0 is a real number, then it will translate into x-intercept. Now, it is not always true that a 0 must be x-intercept. No, it's not always true. For example, if I have fx equals to x squared plus 4, when I try to look for the zeros, I will get imaginary number as plus minus square root of -4. That's plus minus 2i. You see, that's imaginary number, right? So the zeros are x equals to 2i, x equals to -2i. But because both of them are not real numbers, they are not real numbers. So this function has no x-intercept. Okay, so we can say that a zero is very closely related to x-intercept, but not all zeros will become x-intercepts. And when we say a zero, we say the zeros are x equals something, x equals something. It's different from x-intercept. When you write x-intercept, it has to be in coordinate form. Okay, when we say zeros, you don't need to. Okay, now so going back to this polynomial, in this example here, you have polynomial of degree 5. It means this polynomial should have 5 zeros. This polynomial should have 5 zeros. If all of these zeros are real numbers, then they are 5 x-intercepts, but maybe less than that. Okay, it just says that it must have the number of zeros equals to the degree. Okay, now later on when we graph, then px, then px has as at most n minus 1 turning points. So for example, to explain that idea, for example, imagine if you have a linear function. That's a polynomial, 2x minus 1. What is the degree? The degree is 1, right? The degree is 1, invisible 1, right? Okay, now because the degree of 1, then the n minus 1 is 0, which is the number of turning points. No turning points. In fact, if you graph that, it looks like this. It doesn't have any turn. On the other hand, if you have fx, let's say, equals to x squared minus 1, fx equals to x squared minus 1, then it looks like this. Notice that the degree is 2. So the number of turning points is at most 1. Where is that turning point in this case? The turning point is here. This is the turning point. Okay. Now another one, let's say I have fx equals to x cubed minus 3x squared plus 2x. You will see this has the degree is 3, right? Okay, and it has 3 zeros. You will see it has 3 zeros, and all of them happens to be real numbers, so it translates into 3 x-intercepts, and it looks like this. How do I get this? I will teach you later on. Okay, there are 3 zeros, and these 3 zeros happens to be all real numbers, and therefore you have 3 x-intercept, and it has n minus 1 equals to 2 turning points. Now those 2 turning points are this one here and another one here. Okay. Next, far end behavior. Far end behavior. Basically, we want to know as x going to infinity, what happened to the polynomial? Px going to what? As x going to negative infinity, and px going to what value? Okay, that's what far end behavior for. Now, the nice thing is far end behaviors depends only on leading leading term. Leading term a sub n x to the n. I will ask you to memorize the graph. If the n is even and the leading coefficient is positive, if the n is even and the leading coefficient is positive, then the graph will behave like an x squared. So it will be like this. We don't know what happened in the middle, but then it goes up to infinity. Okay, the hint is imagine x squared. Now, in other words, as x goes to positive infinity, when you go very far to the right, the polynomial will go to infinity. As x going to negative infinity, the polynomial still go to positive infinity. The same like the graph of x squared. The graph of x squared, when you go very far to the right, it goes to positive infinity. Go very far to the left, it is still positive infinity. Okay. Now, in short, I usually call this top. This is my own terminology. Basically, when you go very far to the left, you go to positive infinity on the top. When you go very far to the right, you go go to infinity. Now, what happens if the leading coefficient is negative instead? What happens if the leading coefficient is negative instead? Then you will imagine negative x squared. It will come from negative infinity. We don't know what happened in the middle. Then you go down to negative infinity. Okay, so formally, as x going to very far to the right, the graph will go to negative infinity. When we go, x goes very far to the left, the polynomial will go to negative infinity as well. Now, far ends behavior does not describe anything happened in the middle. Like we don't know what happened in the middle. We don't know what happened in the middle. Okay, we just know that if you go very far to the left or very far to the right, it will go to positive infinity or negative infinity. Okay, now in my class, my notation, I will call this bottom. So if you go very far to the left, it goes to the bottom. When you go very far to the right, it still goes to the bottom. Now, what happens if the degree is odd. And the leading coefficient positive, then the graph will look like this. The graph will look like that. To help, you can imagine x cubed. The graph of x cubed looks like this. Which means as you go very far to the right, the function, the polynomial function, will go to infinity. And when you go far to the left, the polynomial function, the value of that polynomial function will be going to negative infinity. In short, I call that bottom on the left, top on the right. Now, what happens if the degree is odd, yet the leading coefficient is negative? Then you basically flip that upside down. Okay, you flip that upside down. So you will see as x going very far to the right, the polynomial will become negative infinity. And as you go very far to the left, the polynomial instead becomes positive infinity. In short, I call that top bottom. Okay. To help, you can say imagine negative x cubed. Okay. So if we look back into this function, for example, this example here, you see that this has a positive leading coefficient, the degree of 5. So the graph of this function, if we do it later on, must behave like this. Okay, if you go very, very far to the right, then the graph will go to positive infinity. If you go very far to the left, the graph will become negative infinity. But then another question arises though, Thomas, why we consider only the leading coefficient and not considering the rest of the polynomial? What happened with the rest? It has something to do with the denomination. You see, when you put a large number, right? Don't go too far. Let's say we put x equals to 10, right? When x equals to 10, this becomes 10 to the 4th. But this is already 10 to the 5th, right? So when x gets larger, of course, this gets larger too. Okay, all of them gets larger, but the number you get from here will be the one contributing the most. Okay, it contributes so much such that this one alone dominate the rest of the terms. Like if you consider this the family, then the leading term will be the one who wears the pants at home. Okay, that's the leading term. So the direction of this family will be depend on the leading term. Okay, just try to imagine, like if you plug in big numbers, like you plug 10,000, let's say x equals to 10,000, then you will see, even though this gives you big numbers, but it is still not as big as the one we get from here. Okay, it has something to do with domination. Likewise, when you plug in x equals to negative infinity, right, it will also behave the same way. Okay. Now that's for far ends behavior. Next, we talked about zeros already. Zeros and multiplicity definition. zero of a function of fx is the number c such that fc equals to 0. So the idea of 0 is not only for polynomial, it's for a lot of other functions. Okay, for it doesn't have to be a polynomial. It can be other functions. Okay, and if you plug in the c and the output is 0, then you call that c a 0. Now, in a polynomial, you will see later on that if c is a 0, then x minus c is a factor. Vice versa. It's like this. For example, when we try to solve, find the zeros of px equals to x cubed minus 3x squared plus 2x, the one that I showed you earlier. Okay, the one, where's that? This one. And how do we get those x-intercepts? Now, to find the x-intercept, we need to find the zeros, right? But then to find the zeros, one technique that we use, and that's what we will do for the rest of this chapter, is to factor it. Okay, so to find the zeros is to look for the factors. That's why you need to know how to do factoring in this class. At this point, if you don't know how to do factoring, you should not move on with this class and you should go back to intermediate algebra. Okay, this is x minus 1, x minus 2. Okay, we do the factoring. Once we write them in factor form, then we say the zeros are x equals to 0. Okay, and then x minus 1 equals to 0, or x minus 2 equals to 0. That gives us x equals to 1, x equals to 2. Okay, now we will see this in 3.3 later on, what we did just now, which already being used actually so far. We have used that, but we will see the theorem in 3.3. What I try to explain here is, first, what is a 0 when it comes to polynomial? And second, what does it mean to say C is a 0 of multiplicity of n? A 0 of with multiplicity of n with multiplicity of n. Maybe I don't use n, of m. A 0 with multiplicity of n is when 0c with multiplicity of n is when x minus c to the m is a factor of dx. Okay, so for example, if I have px equals to x plus 1 cubed, x minus 2 to the 4th, and x minus 5. Then we say the zeros are x equals to -1 with multiplicity of 2. I'm sorry, with multiplicity of 3. Why? Because it happens 3 times there. Because it happens 3 times there. Okay? And 2 is also a 0 of that polynomial with multiplicity of 4. Okay? 2 is a 0 with multiplicity of 4. And then 5 is a 0 with multiplicity of 1. Now, if you get a 0 with multiplicity of 1, we also call that 0 a simple 0. Okay, now we are going to graph this polynomial. But before we actually graph them, let's do sign graph. Sign graph. Sign graph of this px. You get -1, 2, and 5. Those are the critical numbers. In fact, those are the zeros, which means when you plug in x equals to -1, the polynomial is 0. When you plug in -2, the polynomial also 0. When you plug in 5, the polynomial is 0. Now, let's do the sign graph. Let's do the sign graph. Let's say when I put x equals to 10. When x equals to 10, this will be positive, right? This will be positive. This is also positive. Agree? All of them positive. So when x is in the most right interval, then you will get the value here is positive. When you pull x equals to 3, for example, what will happen? When x equals to 3, you get 4 cubed, that's positive. 1 to the 4th, that's still positive. 3 minus 5 is negative, right? So that's positive to the 3rd, positive to the 4th, and then negative to the 1. That will be negative. When x is between -1 and 2, let's say x equals to 0. When x equals to 0, when you plug in here, when x equals 0, you plug in here, that's positive. When you plug in here, this is negative. When you plug in 0 here, that's negative. But to the power of 4, that's still positive. When you plug in here, that's negative. So the total, the product, positive, positive, negative, is negative. Finally, when x equals to, let's say, -4, you plug that in. -4 plus 1 to the power of 3, that's negative to the power of 3, that's negative. And -4 minus 2 to the power of 4, that's negative to the power of 4, that's positive. -4 minus 5, that's negative. So you get negative times positive times negative, that's positive. Now we want to see the following, we will see the following phenomena. Notice that the 0 at -1 has odd multiplicity. When it is odd multiplicity, the sign to the left and to the right are different. Okay. Now, when the multiplicity is even, the sign to the left, to the right are the same. if the multiplicity is odd, right, the multiplicity is 1 here, then the sign on the left and right are not the same. Okay, now which means the following, if, why do we want to know a 0 and its multiplicity? If C is a 0 with even multiplicity, then the sign to the left, the signs to the left and to the right of it is this, are the same, or both positive or both negative. And consequently, because they have the same sign, it also implies the graph does not cross x-axis. If C is a 0 with odd multiplicity, then first, the signs to the left and to the right are opposite. And the graph crosses x-axis. In fact, we can say more in both cases that the graph will touch If it doesn't cross, then it will touch the x-axis or cross the x-axis similar to x to the m of the multiplicity. Now let me ask you to take a look on the following, the graph that I have earlier. That's y equals to, what's that? X cubed minus 3x squared plus 2x. Now notice that the zeros are 0, 1, and 2, right? 0 and 1 and 2. Let me screenshot this. Give me a second. what I want to say is this. Notice that earlier we factor this and we get x times x minus 1 times x minus 2. And the zeros are 0, 1, and 2, right? Okay. And you can see that the zeros are all simple, has simple multiplicity. So the zeros are x equals to 0, x equals to 1, and x equals to 2. All of them has multiplicity of 1. Okay, so what I was trying to say earlier about the graph is the following, that because the multiplicity of x equals 0 is 1, it means when it crosses the x-axis, it will cross linearly. It will cross linearly because the multiplicity is 1. It will cross linearly because the multiplicity is 1. Now, let's compare that to what happened if we have the next one was, what was that again? Sorry, I forgot. X plus 1 to the, or x plus 2. I think x plus 2 to the third, right? And then x minus 2. Let me look at my note better. Oh, x plus 1 cubed, x minus 2 to the fourth. X plus 1 cubed, x minus 2 to the fourth, and then x minus 5. See? Yeah. That's what it looks like. That's what it looks like. Let me screenshot that first. That's what it looks like. Now, what I want to say is this. When you zoom it, for example, at 5, right? When you zoom it at 5, notice that 5 is a 0 with multiplicity of 1. It's a simple multiplicity. So when it crosses the x-axis, it will cross it just like a line. I super zoomed this already. It crossed that graph like a line. Okay, now, but 2 is a 0 with multiplicity of 4. So when it touch x equals to 2, it touched that like an x to the fourth. Okay, it touched that like x to the fourth. And then at -1, because the degree is 3, then it will cross that like an x cubed. It's not a straight line. It doesn't cross that as a straight line. You see, it crossed that not as a straight line. Okay, let me screenshot this. Screenshot and then I go back to our notes. Okay, so you see that this way I can write better. At -1, it's degree of 3. So it behaves like cube. It's not crossing it straight like that. No. It's kind of like it turns, right? It behaves like x cubed. Now at x equals to 5, it is 0 with single multiplicity, simple multiplicity. So when it crosses that, it will cross that just like, it's just like a line, okay? At 2, it has multiplicity of 4, so when it touch that, you know, it's if it is even multiplicity, it will not cross, but it will touch, right? But when it touch, it will touch like an x to the 4. Okay, now that helps us later on. Suppose, for example, something I do super fast right now. Okay, suppose, for example, I need to graph this, sketch the graph of px equals to x plus 1 squared, x minus 1 cubed, and then x plus 2 times x, I'm sorry, x plus 2, okay, x plus 2, x minus 3 squared. Let's say I need to sketch the graph for that. Then from the factors, we see the zeros are -2, -1, 1, 3. Those are the zeros. Let me give you the color. The -2 from here, -1 from here, 1 from here, -3 from here. Right? Okay. Now, and then what happened to the sine graph? What happened to the sine graph? Let's see what happened when x equals to 0. So I try to find the x-intercept. I mean the y-intercept. When x equals to 0, I get 1 squared, -1 cubed, times 2 times -3 squared. That is 1 times -1 times 2 times 9. That's -18. So when x equals to 0, the sign is -18, negative there. Now then, from here I see, oh, 1 is a 0. 1 is a 0 with odd multiplicity. So when it crosses that 1, I need to change the sign because it is odd multiplicity. Okay, and 3 is a 0 with even multiplicity. So when I go around the zeros, right, I don't change sign. -1 is a 0 with even multiplicity, which means when I cross that critical number, I don't change the sign either. -2 is a 0 with odd multiplicity 1, right? So when I cross that one, I change the sign, plus. Okay, then when I try to sketch the graph, my x-intercept will be at -2, -1, 1, 3, y-intercept 0, -18, and the graph will be as the following. If the -infinity to 2, it's plus, means it is from above the x-axis. Between -2 and 1, it is below x-axis. -1 is below x-axis, right? But you see, at -1, the sign is the same. At -1 on the left and right, the sign is the same, which means it's just touching without crossing. It's just touching without crossing. Okay. And then I don't know where it turns. It will be coming back here. What happened at 1? At 1, it will cross. In fact, it will cross, what is the degree? It will cross as an x cube. So it will cross as an x cubed by terms like this. Okay. And then 3 has multiplicity of 2. So it will touch at like a degree of 2. Basically, it will yeah. Notice that from here we see that as x goes to infinity, the polynomial actually goes to infinity. You see that? When you go very far to the right, it goes to the right. It goes to infinity. And as x goes to negative infinity, when you go very, very far to the left, the polynomial actually, the value actually increases to infinity as well. But we only have this situation. It means the polynomial must have positive leading coefficient and the degree must be even. See, right? The leading coefficient must be positive and the degree must be even. Now let's take a look here. If I really multiply this out, what is the leading coefficient? You will get x squared from here, x cubed, x squared. The leading coefficient for all of them is 1. Right? The leading coefficient is 1. And this will be 1 x to the 5, 6, 7, x to the 8. So you see the leading coefficient is positive 1, the exponent is even. Thomas, how do you get that 1 x to the 8 blah blah blah? Try to multiply it out. Don't do it in full though. Don't do it in full. This is x plus 1 squared, x plus 2, x minus 1 cubed, x minus 3 square, and this is to the 4th here, I guess. I don't remember. Oh. I think I'm missing something. Oh, x plus 1 squared. X plus 1 squared. So I was right here. It was a square earlier. Now, notice that when you FOIL this, you will get x squared something. Right? Multiplied by x something. And when you FOIL this, you get x cubed something. When you FOIL that, you will get x squared something. Right? Now, when you multiply x squared by x cubed by x squared, you will get 1x to the 8th. That's how we know that the leading coefficient is positive and the degree is even. Now, all of these basically just informations without computations. You still need to know how to factor them. What I teach you here, most of them are actually recognizing a polynomial. You know what is the degree, leading coefficient, leading term, constant. What is the zero and the multiplicity, the number of turning points. If you have a polynomial, can you tell what is the far end's behavior? Okay, and what is the effect of multiplicity when it comes to sine graph and when it comes to the graph? In fact, how does the graph behave near a zero? That's basically what we learn here for now. Okay, next, the harder one, division. First, long division. I still need you to know this. Long division of polynomials. For example, if we have let's say we have, for example, 2x cubed plus 3x squared minus 4 divided by x minus 2. Let's say we have this polynomial to divide by x minus 2. Long division is done in the following way. The numerator, just like before, will go inside the house. The denominator will be outside the house. Is it okay? That's one. Second, be very aware that the polynomial has to be in descending order. The polynomial has to be in descending order. Actually, both of them. In descending order means the degree has to be from the highest to the smallest. Okay, so we have x minus 2 as a divisor, and the numerator will be as the what you call that, dividend, 2x cubed plus 3x squared. Remember the descending order, okay? Such that if you have a skip, then you need to put that term that you skip as you need to place. You need to have a placeholder. Okay. Now then, from here we divide. We ask ourselves, okay, x minus 2 times what give you, maybe to be more precise, x times what give me, x times what give me 2x cubed. X times what give me 2x cubed. You get 2x squared, right? Okay. Now 2x squared position is here. Now then you ask yourself, okay, 2x squared times x is 2x cubed. 2x squared times negative 2. So basically you will distribute this against this term. Okay, and you will get minus 2x, I'm sorry, minus 4x squared. Now then, just like a regular long division, we will subtract. So you will subtract 3 minus negative 4. That's positive 7. This is 7x squared plus 0x minus 4. Now you repeat the process again. X times what gives me 7x squared. That will be 7x, right? But here, x times what give me 2x cubed. That's 2x squared. Now the next one is 7x, so I have plus 7x. Then distribute this 7x to x and to negative 2. Okay, 7x times x, as we expect, is 7x squared. 7x times negative 2 is negative 14x. Then we subtract. 7x squared cancel. Now 0 minus negative 14 is positive 14. This is 14x minus 4. Then last, x times what give me 14x. 14. Okay, so plus 14 here, I get 14 minus 28. 14x cancels, negative 4 minus negative 28 will be 4. So this is 4. Now, therefore, the quotient is 2x squared plus 7x plus 14 plus 24 over x minus 2. That's for long division. Now, long division can be used in every case when we have polynomial divided by a polynomial. Let's see a more complicated case. Let's say if I have the same one, 2x cubed plus 3x squared minus 4, but this time I divide by x squared, maybe plus 3. X squared plus 3. So I will get 2x cubed plus 3x squared plus 0x minus 4 divided by x squared plus 0x plus 3. Remember, it has to be in descending order also for both of them. Okay, and be aware if you have any skip. Okay, be aware with any skip. By the way, I thought, remember I told you that you need to, I would like you to watch the lecture video. Okay? Because I thought the same thing at my pre-calculus classes at West LA College at Santa Monica also. Okay, so the lecture video I want you to watch actually from, in this case, from Santa Monica. Now, when I gave this test at Santa Monica, a lot of people actually make mistake because they missed this one. And they missed this one. Don't miss them. Okay, those are important. Those are important. Those are important. You need placeholder so that you don't get confused with the places. Now, let me start. And x squared times what give me 2x cubed. Two x, right? Now, the place for x term is here. So I put 2x there. Now this 2x should then be distributed to each term. Okay? So that will be 2x cubed as we expect, plus 0x squared, plus 6x. Then I subtract. When I subtract, the first term disappears, cancels. The second term actually quite easy. 3 minus 0 is just 3, 3x squared. Now 0 minus 6 is negative 6 though. Okay, so this is negative 6x and then minus 4. Now then x squared times what equals to 3x squared. Times 3. So I plus 3 here. This will be 3x squared plus 0x plus 9. When I subtract, I get negative 6 minus 0 is still negative 6. Negative 4 minus 9 is negative 13. Now, I will stop here because the degree I have left is already less than that. Okay, once the degree here is less than that, then I know I can stop. The quotient is 2x plus 3 plus negative 6x minus 13 over x squared plus 3. Or if you factor the negative on the top, then you get 2x plus 3 minus 6x plus 13 over x squared plus 3. Okay, that's for long division. Syntactic division, which is very, very important for this course. Syntactic division can only be used only when dividing by x minus something. Okay, x minus something, x plus something. So the divisor has to be a binomial degree of 1 leading coefficient 1. Notice that long division can be used in every case. Long division can be used if the divisor is x minus, in this case, x minus 2, or if the divisor is x squared plus or minus something. Okay, but synthetic division can only be used if the denominator is x minus something. Okay, now, example, the one we have earlier, 2x cubed plus 3x squared minus 4 over x minus 2. Now, the way synthetic division is being done is the following. We will draw a rectangle like this, in which the first row is the coefficient of the numerator. The coefficients only, in descending order. Coefficient in descending order. Okay, so the coefficient in descending order will be 2 for degree of 3, 3 for degree of 2, 0 for degree of 1, negative 4 for degree of 0. And then we will put a number here, which is this number, 2. Remember, if you divide by x minus c, then the c is what you put there. In this case, you divide by x minus 2, right? So the c is 2. You put 2 there. Now set it up correctly, though. Please set it up correctly. Now then, the way the syntactic division is done is the following. The first number always being copied down here. You always copy that down there. Always, always, always. Now then, we will do the following work. Whatever the number you have here, multiplied by that 2, and then you put it there. Okay, 2 times 2 give me 4. And then you add. Repeat the procedure. 7 times 2, 14, you put it here. And then you add. Then 14 times 2, that's 28, you put it here. Okay. The last number, you box it. Oh, Thomas, I'm lost. No, don't worry. Don't worry. I will repeat it. First, the number here, you always copy it down. Always copy it down. Then the procedure will be this guy multiplied by that, put it here. And then you add. You add, multiply by 2, put it here. Okay? And then you add, multiply by 2, put it there. And then you add. Now, this is what we get. So how do we interpret those numbers? These numbers here, okay, these numbers here represent, let me use blue, represent the quotient. It represents the quotient. So this is equals to 2x squared plus 7x plus 14. Notice that this 2 here is degree of 3. So this must be degree of 2. Let me say it again. If the original polynomial that you divide is degree of 3, then the 1 down here must be degree of 2 because you divide by degree of 1. Okay, now how about the remainder? That's plus 24 over x minus 2. Let's do more. Let's do more. Example 2. Suppose I want to divide 3x to the 4th minus 10x squared minus 2x plus 4 all over x plus 3. The numerator already in descending order, but be aware we have a skip there. Degree of 4 has coefficient 3. How about degree of 3? Coefficient 0. Degree of 2, negative 10. Degree of 1, negative 2. The constant is 4. Okay, so be aware with this. Now, how about the number on the left-hand side here? What should I put there? I need to put negative 3 because we rewrite this as x minus negative 3. So my C is negative. That's the setup. Don't rush to the answer, no. The setup has to be correct first. The setup has to be correct first. The setup has to be correct first. Now then, I bring this down. This is 3 times negative 3 is negative 9. I add. Times negative 3 is 27. I add. Times negative 3 is negative 51. I add. Multiply, that will be, oh, it's 159 positive. So when I add, I get 163. So the quotient is 3x cubed, 1 degree less. Degree was 4, now becomes degree of 3. Minus 9x squared plus 17x minus 53 plus 163 over x plus 3. let's say I do, I guess this is one of the last example I do from here before I move on to the next topic, number 46. Number 46, 3x cubed minus 4x squared plus 5 over x minus 3 halves. Oh shoot, this looks so ugly. Can I use long division here, Thomas? Yes, you can. But why? Syntactic division was invented so that dividing by x minus something can be easier done. That will be the setup. Now then, the first number, I drop it down, that's 3, multiplied by 3 half is 9 half, which is 4.5. So when I add, I get 0.5. No, I don't want to make it decimal. Not a good idea. Just leave it as 9 over 2. Now, negative 4 plus 9 over 2, that's negative 8 halves plus 9 half, that's positive 1 half. Now, positive 1 half times 3 half is 3/4. Add, multiply by 3 half, that would be 9 over 8. Now 5 plus 9 over 8 is 49 over 8. So this is equal to 3x squared minus 1 half x plus 3/4 plus 49 over 8 big over x minus 3 halves. That's for syntactic division. Remainder theorem. If polynomial px is divided by x minus c, then the remainder r is equal to pc. If px divided by x minus c, then the remainder is pc. Let's show what it is saying first. Proof. Let px divided by x minus c gives quotient qx and remainder r. So basically px divided by x minus c give us this quotient with remainder r. you can try to imagine what we did earlier. One of the example we did earlier was this one. Let me just quote that. Actually, I prefer, no, I'm sorry, not that one. This one. For the wrong. That's for example. And then we get this is equal to 2x squared plus 7x plus 14 plus 24 plus 24 over x minus 2. So the qx is this. This is the qx. This is the quotient. This is the remainder. Okay. The one on the right hand side here, just an illustration. Now, here's the thing. We will multiply both sides by x minus c. If I multiply by x minus c, then the left-hand side px is equal to, on the right-hand side, qx times x minus c plus r. Okay, so to illustrate what we have on the right-hand side, it means 2x cubed plus 3x squared minus 4, the numerator, is equal to x minus c times 2x squared plus 7x plus 14 plus 24. Okay, don't forget that the quotient qx and the remainder 4. Now, what this theorem says is the following. If you want to find the remainder, you can just plug in c into x. Notice that pc equals to qc times c minus c plus r. Now the thing is, this is equals to 0. Therefore, the remainder is equals to pc. What does it mean? What does it mean? Consequently, if we want to compute P2 for Px equals to 2x cubed plus 3x squared minus 4. Right? If you want to compute P2, then we have now we have two methods. The first method, you plug that in. P2 equals to 2 times 2 cubed plus 3 times 2 squared minus 4. That's 2 times 8 plus 3 times 4 minus 4. That's 16 plus 12 minus 4. That's 24. That's one way. The second way, you do synthetic division. 2, 3, 0, negative 4, divided by x minus 2, and c was the quotient. I mean, what's the remainder? So then you know that P2 equals to M4. Okay. Now, what is your suggested homework from here? On Thursday, we will redo this again. We will go on further from here. Okay, but suggested homework, things that I really need you to do is 3.3, number 11 to number 45. 11 to 45 for the 3.3a. And then 3.2, 3.2a, because I'm not done with that yet. I would like you to do number 9 to number 15, the matching. Number 21 to number 29. And then number 35 to number 49. Okay, now we will continue on this on Thursday. See you then Thursday. Oh, don't forget to watch the lecture video I told you from my from the discussion. Okay then, bye-bye.